even after the COVID, it wasn't ready for that. So we were actually opening another laptop for actually holding the online meeting, and then there was always problem with the audio, and so.
So, I forgot to ask you, were you born in Krakow?
Yes.
So that's your hometown?
Yes, that's my hometown, and also part of my family is from there. Saying like really from at least like something like 3 generations back from me, or maybe even more. But
so you live in this old house?
No, we moved from the center, or my grandma, she was living there for a while, but then and right now, it's really hard to live there also because the tourists and so on.
Right.
But
so Krakow still has its old town, right?
Oh yeah. No. This is, I think, the unique thing about Krakow, that is, UNESCO heritage and so on. That and really during summer it attracts so many tourists that it's just crazy. So I really enjoyed the old town, but out of tourism. Yeah, just sometimes when the bad weather or it's cold, and let's say you end for some different reasons, you end up there in the morning, especially like you see the main market square just empty, and that's then it's just picturesque, because otherwise it's like, it's still not level of India, but people will approach you, propose you something, and
so Warsaw was like more concrete and very Stalinist architecture.
Yeah, because most of theirs was just destroyed, and then they were rebuilding, and then what is for me nice about Warsaw, they have space. Saying like these old towns, everything is a bit narrow streets, everything is kind of cramped there, and there in Warsaw we really have, which is disadvantage and advantage, because still they get traffic jams, of course, but at least the area is, let's say, easier to flow, and also the distances are higher. That's the you can in Krakow, it's still relatively large city, so it requires a bit of walking, but you can do it. In Warsaw it's more like public transport if you want to get from one point to the other. But this also makes it a bit more modern, attracting a lot of foreign companies, and being the basically richest city in Poland. Like still, for some reasons, Krakow, we don't have so high pace, but the pricing of the accommodation is high. So in terms of cost of living, Krakow might beat them relative to the salary.
Hi, so before we start, a couple of announcements. Sorry?
I have no idea what this person will
Okay, whatever. So who are the people? You have to tell me.
Sorry. This person.
So Vaishnavi and Akshay and Roshni and Nimal. Can you just finish filling up your TA form and give it to Nandini by lunch, because the office says that after that they'll close their accounts, and too bad. Okay, so just send it as soon as you can, okay, so that we can submit it by lunchtime. All right, these 4, right? Okay, all right. And another announcement about the weekend. So we have about 7 or 8 people who have signed up. So our office said that given this, they will just use the regular shuttle, which takes the institute students who are staying there and brings them to IMSC, instead of having a separate shuttle for the workshop participants. So that one leaves at 8:30. Okay, so 1 hour after the scheduled thing, so you can sleep 1 hour later on weekends. So it leaves at 8:30, and then it starts from here again at 8:30 p.m. Okay, and the other thing is, so you can take that shuttle, to the regular shuttle, to come over to IMSC campus and then leave from IMSA campus. And the other thing is that instead of having special food arrangements on the upper floor, you can just use our regular institute cafeteria. So when you go to the billing counter, just tell them that you're here for the workshop and just give your name. So they will just note it down. You don't have to pay anything. Is that understood? So breakfast, you just come over in that shuttle, get breakfast. Lunch will be from 12:45 till 1:45. It's officially till 2, but don't go after 1:45, you won't get anything. So then I think dinner is from 7:30 to, again, officially 9, but by 8:30 food runs out. So but anyway, 8:30 the bus would leave, so you have to finish your dinner before that. All right? Any questions about that, the weekend program? Okay, so if not, it's my pleasure again to invite Marcin to give the tutorial part of it, and this is the final of his lectures in the workshop. So, Marcin.
Thank you again for having me here. It's very enjoyable meeting. I've had a lot of discussion, and that's great. Yeah, it should work. Okay, now it works. Today is a tutorial. It's a bit more informal. The idea was I wanted to show you that this positional error that I introduced and positional information during the first talk, it might sound something like a bit complex, but for positional error, you can do many of those things like back of the envelope calculations. So I will start with doing some calculations, and maybe you can help me at some points there or make your guesses about what's the outcome. Later on, we will visualize some of the things, and at the end, I will show you how to relate it maybe to research work. Okay, so the problem I have chosen for today is, we have already seen, morphogen gradients. The morphogens are produced as the specific source regions, and then they are degraded and spread across the tissue through diffusion. Now, I think in one of the talks, I guess by Micton, we had this, and part of that was already solved, but still, let me switch it on. I want us, it's fine. I want us to consider the consequences of the shape of the morphogen profile on the positional error. Okay, so first, here you see the well-known French flag model. Here you see the diffusion equation. There is degradation term, and we will consider 3 cases. Either there is no degradation, maybe not so biologically relevant case, but still, then linear degradation, the most common, and then the nonlinear degradation. So for the first part, I will just quickly calculate, solve this equation and get the profiles. But first, before maybe solving, any guesses about what would be the form of the solution? Saying like, let's say we don't have degradation. There's just diffusion term. So what would be the morphogen profile? And is it going to be, I don't know, some quadratic thing or constant thing? Just make your guess. I think I heard something like linear. Yeah, linear. Okay. The answer is linear, but I will prove that. The other case, and this is, I would say, easier to guess because we already saw bicoid, we already saw sonic hedgehog, BMP. So what's your guess for the second case? What would be the shape? Yes, thank you. That's the right answer. And the quiz continues like the third case. We have non-linear degradation, saying like squared here. So we already had linear, morphogen profile. We already had exponential. So what could be next? Close, but no, that you can get. I don't know if you would add some. Okay, if I'm not mistaken, you would get constant degradation. That would not depend. Then you would get some x squared. But no. Okay, so in the third case, it's a power law decay. And the power law decay would be with square here. So this is, one could solve that directly by integrating, but I would prefer here, and it's also the faster way, you do educated guess about your solution, and then you just check what are the A, B, these are some constants, and we will determine them based on the boundary conditions. So the idea is to have system where here at the left boundary there is a source. It produces morphogen at a concentration M0, and then, okay, depending on the solution, depending on the case, it can either be this linear degradation. There is tissue length L, and then based on this, we will determine the steady state solution. So I'm not going to work with the full temporal dependence. We are interested in what happens after a long time. So after a long time, this derivative over time, so your morphogen profile is not changing. So we will solve this case, and then M, which was here a function of space and time, becomes basically function of space. Okay, the distance measured from 0 here to L here. So let's tackle the first case, the very simple one. So what we are left with is just such equation. And now, what's the usual strategy? You get the derivative of your morphogen profile. In this case, you just get what? If I take the derivative of the linear over x, I get, so the constant gets gone, and I'm left with A. And if I get, that's just to warm up. The second, it gets me 0. So if I plug it here, then it agrees. This way I checked, okay, my solution fulfills this equation. And now I want to determine A and B. So I use my two conditions. M at 0 should be M naught, and M at L should be 0. So it's like, biologically you could think that at the tissue there is some sink that just, the morphogen gets flushed away. Again, this, I would say, for me, is like working example. I would say biology works more like this, but still, let's do it. So then, of course, this condition, or maybe this one, what it will tell you? It will tell you that if you input there, M0 equals to B, and having M0 there, you use the other condition, so 0. If at some point here, I think everything is clear. Again, we are warming up. Just let me know. So from this, A is equal. So we got our solution for this first case. Let me maybe write it here. That So indeed, for 0, it gives you m0, and as x gets to L, it's gone. Now, let's quickly go to the case 2. So now we had this general form, but there is one observation that we could already use to simplify, and this is this last statement. So I could solve it for L that is finite, but I could also go with L to the infinity already, because that will largely simplify my calculations. And then what happens? Exactly. A should be 0, so we are left with basically our ansatz. So we just need to determine B and lambda. Okay. Actually, I noticed that in Mictum talk, this was like this. So maybe let's do it like this, because then lambda would have dimension of the unit. Okay? It doesn't matter. Saying like lambda there, I could redefine and call it lambda tilde, or there put lambda tilde, same. And now we again do, okay, first thing, how to determine lambda. So you do it by checking whether this is the solution of your diffusion equation at a steady state. So again, I write it for the steady state. And then what I need the second derivative of that, which is, is one of the simplest thing to do. If you have exponential function, then the derivative of it, you just take what is in the exponent, beta, and then the second derivative would be just and now if I plug it here, then what I found is for this to be the solution of my set of equation, and this is fulfilled. When this is fulfilled, only when my gamma is equal to diffusion divided by degradation squared. So you see that just get rid of those, then this gets to the other side, lambda squared, and then you take the square root. So we got our characteristic length, so the decay length. So we are left just with this parameter, but this is even simpler because we use our condition for concentration at x equals 0, and then this should be, m naught, which means here I put 0, so this is 1, and this is left with m0 equal to b. So the solution I get where let me write explicitly over degradation. And again, we could check at L that goes infinity, it goes to 0, everything works. And also this has dimension of unit, x divided by something with the dimension of unit gives you non-dimensional quantity. So that would be the solution for the second case. Okay, and now we have the last one, which is a bit maybe more demanding in terms of taking derivatives, but nothing else, you know, is, yeah, the procedure is exactly the same. So we again start with the steady state. So solution, we want to look for the solution in the steady state. What we need the second derivative. So we first get the first derivative of our ansatz. This would be minus 2a sorry, this, and then we take another derivative, and we end up with 6a 4. Okay. And now, to determine a and b, what we would like to have is okay. First, let's see whether it works for our steady state equation for the steady state. So what else we need? We need to square our ansatz, but let me do it on the fly. So we have this, say d minus degradation, and then we have this squared and this squared, which means it's to the power 4, which is good because then we see it will work, saying, you know, those two should cancel out. So we have and with this, you know, a cannot be 0, so basically a is equal to, okay, so I got a, and now I want to get b, and to get b, let me look how, let me again use the condition for the value of the morphogen at the source, or at the boundary, and the ventral boundary x0. So this one, and now I plug it in. I already have my a. So m0 is equal to okay. And now again we have beta, okay, squared. And now, okay, we take the square root of k. Okay, two solutions are possible. So which one I should pick? Should I pick the negative or the positive root? Positive. And why? It's a good guess. Good intuition. Yeah, it will make problems, but why it will make problems? That's also good intuition. Now, so x here. Yeah. So in principle, you know, if you would have negative b, then okay, because I'm considering x going to infinity for the right end, it goes through all the positive. So of course it would hit at some value this, and it would cause a problem. So that's why I pick positive, and then yeah. Okay. Let's just say, because this cannot have a singularity, or we want it to not have the singularity, that's why we pick the positive solution, and then our solution is following. Let me, okay. Yeah, it's A is 6 kappa, and then this is the square root of it's 6d over gamma. What you can also notice here, when you look at this, and you look at this, oh sorry, this was supposed to be gamma. Yeah, then this is characteristic length scale, so if I would like to rephrase that, but just, this is like an observation that you get, you know, something that has units of length squared divided by something that we also have units of length scaled. So possibly it's, you know, some check whether you didn't make a simple error in your calculation. Okay, so we arrived at the solutions, and yeah, before I visualize them, this can be done quite quickly. I want to add one more thing, because we already calculated the derivatives. Right now, it's really straightforward to calculate the positional error for your curves, saying we have solution 1, we have solution 2, and we have solution like 3. This would be this power. I can show you that, yeah, let's say, roughly like this. It doesn't just, exponential falls just more quickly than the power law. So 1, 2, 3. And now we would like to, what we would like to do is, let's assume that our morphogene profile has some fluctuation in the gene, saying like this is like the standard deviation of, if this is noisy, blah, 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 like this, and all can be noisy, then this quantifies, okay, standard deviation would be like this, plus minus this. And it doesn't change, you know, for simplicity, it's not dependent on the concentration, it's just constant noise. So now I need a bit of space here, but let me just leave, okay, let me just leave this. And nah, let's do it all. This will be more clean. So we want to calculate this quantity. And this depends on your position. Okay, this is the positional error for a single concentration gradient. Then okay, then we take our first case, and what we have? The derivative is just this loose term. So for the first, times m0. Sorry, not times, but it's I should take the inverse. So it's by m0. And for the other one, okay, this will get here. So again, the derivative taken with the absolute value would be m0 over this times, yeah, the exponent. So the value here would be, yeah, now I take the fluctuation in the level of my morphogen, and now I need to invert that. So first thing you can notice, because I need to invert, this is now positive. And okay, for the third case, I would say we will see it during the visualization. You can do the math. The point I want to make here is that there are two things. First is which one, or okay, let me phrase in the question. Which of these two morphogens will give you a smaller positional error at the end of the tissue, or at some large distance from the source? Was it going to be the linear or the exponential? Linear, yes, because linear is basically constant. It doesn't depend on your position in the tissue. And yeah, and the exponential will, of course, grow exponentially. But now, okay, now, okay, okay, I can put some values to those. Then this exercise is a bit easier. But if you would have now ask which would give you the better precision or lower positional error at the source, so at x equals 0. Okay, it might depend on the numbers, but at x equals 0, this would be, yeah, this would be this. So, okay, depending on how large is this guy, yeah, and we will now do this exercise by putting some simple numbers to simplify things and see how it all gets visualized. Okay, yeah? Sorry?
This relation between the variance.
So all this, so for this, to calculate that, you use, you assume it's a Gaussian, saying like your noise is given by the standard Gaussian distribution, or just by the normal distribution. It's this idea of positional information. Okay, the Gaussian there comes like you want to calculate the positional information, then kind of the Gaussian distribution maximizes the entropy. So you want to have some lower bound, but in principle, it's like you could have a different distribution, but then this formula for positional error is not so nice. Okay, so
yeah. So it seems like the ones which the profile which will be having a steeper slope, that will give a greater precision. I mean, in that
yeah,
so,
exactly.
Yeah.
That's one of the take-home messages of that. So let me quickly just show you. These are the profiles that we derived. I derived with your help, like defined in Mathematica notebook. And now, yeah, I think everything on the Blackboard should be fine. Saying like agree with that, and then we make simplifying assumptions. Just to to do some back of the envelope calculations, we say L is equal 6. Then, yeah, gamma would be 1. Then D would be 1. Then M0 would be 1 in the appropriate units. Then also this guy, so our lambda will be 1. And then you see that if using these simplifications, we see that this, okay, and the noise we set, okay, but here we don't need to set the noise. This is divided by 6. And here, this is just, sorry, this is not divided by 6. This is just, maybe I, M0, yeah, if I'm, no, this is just the error, that's fine. And here, what you get, you should somehow get, okay, let me see if yeah, something is, okay, anyway, let's see. So far we are doing well. So what you see here is, okay, sorry, I just scrolled too much. Okay, we go step by step. So this is the, yeah, of course, I forgot here, we had this here. Yeah, you should tell me. I actually took the derivative and I forgot to include L here. So it should be something like this. Okay? Saying like you take derivative of this, then you end up with this, you take the absolute, then you switch it. So it's even like, okay, now it's good. Now we are done. And now this is, and now you see that at the source, this would be much higher, and here it would give you, so this is your linear, this is for the exponential. Okay? Okay, I should, I'm used to using it differently, but let's okay, so those are our profiles, and now we take the concentration threshold. So now, think about that. You have these different profiles, and you want to apply this concept of French rag model by Louis Wolpert. So you need to decide about some thresholds. Let's say we want to divide that into 3 equal stripes. Then what you do, okay, here I had one more observation, but we already had that what's the concentration at the ventral end, so the right end of the dorsal end, so the right end of the tissue. At L, linear is 0 because, yeah, we set this to 0. Exponential would be really low. So I would say, yeah, this assumption about L going to infinity works. And power law, I would say it's not so low. But, yeah, so probably, yeah, if one would be fitting some data, one should take this into account. But now getting back to the idea of the thresholds. So we want to divide we want to use this gradient to have 3 equal stripes. And then the thresholds, let's say there is some generic regulatory network interpreting the signals. In case of linear, that would be equally distributed here. But you could already see here for exponential, you know, there is here huge gap. So for a cell, probably it's easier to distinguish between the two. Okay, now then you can imagine that if it's noisy, then it's even better to have a large difference than between here or here, saying like exponential is this one. Yeah, linear decay means exponential profile. So here I calculated that, but the exact values are maybe not so important. This is at x equal 1, but if you want to have 3 stripes, those would be the thresholds. And already you can see that if your concentration is 1 here, then if you want to specify something here with this exponential, you need to go 2 orders of magnitude lower, which already means that probably, yeah, this might be still fine, saying like cells could interpret very low numbers, but if you would go, I don't know, 3, 4 orders of magnitude, that's it. Even with very fancy biomechanical, okay, biology is very, sometimes, yeah, things could be refined and so on, but I would say as a rule of thumb, it would be difficult to have mechanisms interpreting signals over more than 4 orders of magnitude. So then I calculated the difference of the thresholds, but again, this we covered, and you can see that if the difference between thresholds is on the order of your noise, and let's say the noise would be something like 5% of your concentration at the source, then basically there is, yeah, this thing will not work. This is just below threshold. And of course, later on, this noise might depend on the concentration. So I'm not saying it. This is like a toy model. And now positional error. We solved that. Yeah, and we got good, in the end, good examples or good solutions. And then if you, again, you could calculate at the x equals 0, linear is constant, exponential, doing really great, close to the source, but then getting worse and worse. Here, probably linear would be the best. Yeah, and at the dorsal end, so at the end, exponential is basically, I would say it's meaningless because it gives you values larger than the length of the tissue, which was 6. And now let's maybe complicate, make this example more realistic in the sense that we now want to consider cells here, and we say, okay, over this 6 in arbitrary units, we have 30 cells. And so each cell would have a cell diameter. If I now divide 6 by 30, I get 0.2 in my arbitrary length units. And now let's indicate this 0.2. So here you see the positional errors for these different cases. You could see, it's linear scale. You could see that early on, the exponential and power law are doing quite well, but already here, and this is 0.2, so that's 1 cell diameter precision. This is already not enough, and then later on it explodes. But it still means, just using 1 exponential, you could probably, 1 tick here is one cell. Okay, so you could probably specify quite well 6 cells, and then with some small error, probably a few more, but that's it. And now if we plot that in the log scale, okay, just replotting, but yeah, you could maybe appreciate that this gets under 1 cell diameter precision. And now let's do the final exercise. Okay, here I have the solutions, but the thing is now how to improve that. And to improve this positional error, so So in terms of maybe design perspective, as you have seen in my talk, but also in Drosophila, you often have opposite morphogen gradients. So again, in my research talk, I gave this, basically the formula for this time positional error for two gradients. Then it was BMP and sonic hedgehog. That was the square root, and here you had like squared. Okay, I will write it in a simpler form. If this we call left morphogen gradient, so this would be something like ML. This would be something like MR. Then this.
Hi, Marcin.
Yes?
Before you go on to the opposite gradients.
Yes?
So I'm just trying to understand the implications of what we've already calculated.
Okay.
So those three gradients.
Okay.
So if an embryo was allowed or subjected to exhibit these three gradients, let us say,
Okay.
linear or exponential or power law. So an ideal embryo would like to exhibit to reduce error, exponential close to the source, exponential or power law, and far from the source, it would like to have a power law profile. If that is acceptable
I
to the
would
embryo.
say, depending on what's the embryo, okay. I would say maybe, yeah, saying that, but already it's about what the level of patterning precision the embryo is, feeling well, or the evolution selected the embryo to have the pattern with the specific precision, saying, assuming that this patterning precision is some selective, feature, that it undergoes adaptation. But as you brought that, I would actually switch to, because I wanted to answer that one with this question, because expecting that with this slide, expecting that someone might ask, so thank you for that. So if you have an error, positional error, so what does it mean for a cell? Now we have, this is the distribution. We were calculating this guy, okay? We had L in some other units, saying like we set it, but in principle, this is the width. This is the positional error normalized to have it in the relative units. And these are the cells. So if this positional error would be localized, this is the Gaussian. This is basically the uncertainty that the cell has about its position. If that would be localized within, okay, this is the center of the cell, and the other cell is in the distance d, roughly cell diameter. So if that thing, this whole Gaussian will, be in that stripe, then the cell could make an ambiguous decision. So that would correspond, forget about the blue curve. Here, this is taken from, this is actually an example with Drosophila would correspond to the green, and blue would correspond to this plot, the arrows. But we are not interested here in positional information. We are interested in this red curve. So early, there is no error. But as we increase this positional error, the cell is more and more likely to make the error in cell-fate specification. So answering your question, maybe in the embryo, if the embryo could afford for higher in precision in the tail, maybe it's not bad to already, because for maybe design perspective, having exponentially decaying gradient is just easier. Just degradation of you don't need to involve any fancy mechanism for this nonlinear degradation. Maybe if you can, biochemically, yeah, the power law would be better at larger distances. If for some way, the embryo could get linear, then even better. Like sometimes you have this scaling of the morphogen profile. So, there are molecules, we consider here just diffusion. but you can imagine that there is some shuttling, and as embryo grows, this actually the decay length is not constant. In the spinal cord it is, but there maybe this can be extended and hence provide higher positional precision or lower positional error, because it's here it's probably it depends. Saying like 0.2 would mean 1 out of 5 cases the cell would make a mistake. Like if you would treat this probability and okay, there might be also mechanisms that correct that by cell-cell contacts. So saying like if cells are in the environment composed of different cells, maybe they sense what is in their neighborhood. Okay?
Sure, sure. I just have one more question. So
Yeah?
the error in this morphogen profile, it's coming mostly because of noise in the production rate, or?
Oh, that's, there are various sources of, I think one of the things, yes, saying like you could say there's a variation in the amplitude, but, there are other, simply the way the tissue is organized, I don't know, due to, so you should think about this morphogen. I'm always like, to plot the curves, but those are actually molecules. They are spreading there. It's unclear, whether there might be some issues related to how whether the tissue is, very permissive for this flow of the morphogen, whether there are some, so there are nice reviews about, what affects the formation of this morphogen profile, and also nice reviews about what affects the noise. So there are, in general, many sources of this intrinsic noise. Okay. So just to conclude, or before, I will still do this one more calculation, but just to give you idea that was the formula we got, and then if you do the math. Again, if that would be L, dx, and that would be, okay, this was 2. Okay, so basically this is the positional error of one of the gradients taken like inverse of that squared. This is one positional error. Okay, you could also, call it like using this nomenclature of x, positional error of from your left gradient, then let me write the full one. So you have the full so this is of the right gradient. And now if you say, let's assume, as in our toy model, that both of them have the same magnitude. One important thing, here you have L minus X, okay, because you are going from the other direction. So if you assume that they are identical, let's take our example, let's take our exponent. So the exponent here was, or maybe, this one, much even easier. Or exponent in the middle, that would also give the positional error the same. So now let's do this calculation for both. And if I just write it down, then I have, so what happens now, I just need to calculate, super simple thing, and where this was my error for, I just assume the linear case, and this would give you by the square root of 2. And this is just saying if those two are identical. So it would happen for all positions in the linear, and it would also happen exactly at the center for exponential. And now, just to conclude, let's get to this. Yeah, these are exactly, I used that formula, I plugged in what we calculated, and now what you can see, yeah, is you get a dramatic decrease of positional error if you have both morphogen gradients. And this is even better seen if we now go and redo this plot in terms of cell diameters. So I simply, before I had space divided, you know, or the cell diameter was 0.2, and now you could get, if I replot with cell diameter, you see that, okay, here, you know, 5, maybe 4 cell diameters by exponential simply by adding another one, versus what we had here, like 100 cell diameters, which is, you know, biologically meaningless. And I must say this example, it was close to saying like, if you would now want to do this math for the case of the morphogen profiles in the spinal cord, there the decay length would be something like 20 micrometers. L would be something early on, at the early stages, something like, yeah, from let's say 100 micrometers to probably, I don't know, 150 maybe, or 120 micrometers. So if you divide this by this, it will give you 6, roughly, you know, in terms of arbitrary length units. But there are fewer cells. So here I said 30 cells. Here you would have, each cell would have cell diameter of, yeah. Cell diameter in the spinal cord would be 5 microns. So we would have something like 20 cells. And so we are, yeah, in a very similar range, and so you could show that, and okay, also the error there might be slightly smaller or larger, but it proves that just by having 2 morphogens, you could significantly reduce your positional error and make it, okay, here, in this case, maybe non-uniform, but at least very close to this, you know, not single, but +3 cell diameters will work. And you could, yeah, in principle, okay, I use Mathematica to visualize it, but there is no reason, you know, just to continue this calculation just with the whiteboard or blackboard or whatever. Okay, and with that, and yeah, I want to, yeah, the take-home message basically, the 2 morphogens significantly improve the position readout by the cells in the tissue. Thanks. Yeah?
So I have 2 questions.
Great.
So here, when you were calculating all of this positional error and everything, we did say that a linear gradient has a significant advantage over an exponential, right? A single exponential morphogen gradient, but then introducing 2 opposing gradients does well when it comes to positional error. But then a linear gradient would also have a significant advantage when it comes to scaling, right? But an exponential wouldn't. So if you have 2 morphogen gradients, opposing ones, how do they do when it comes to scaling? So in a single case, I know that it's not easy to scale an exponential gradient, right? So what happens in the case of...
This is like excellent question also because, you know, what kind of, yeah, it's about this scaling mechanism in different developmental organisms. And, you know, for some, we understand it. There are many models proposed. But that's one of the reasons why if you can get scaling in the embryo, then it makes the whole, you know, readout procedure much easier, because if the cell is sitting at a certain position, you know, it just reaches very similar concentration all the time, the tissue is growing and so on. Yeah, having said that, in spinal cord, for instance, you don't have this scaling. This is what we observed, this is what we quantified. So it got us thinking, you know, how this pattern is emerging. And then two things. One, the pattern is emerging through gene regulatory network that interprets signals over time. And what we saw is that when they move away to extent that in the middle there is almost no signal, so high positional error, you already specified the fate. So the network already took like the signal from early time points and already specified the output pattern. And we could also show, like in simulation, that if you abruptly remove the morphogens after, let's say, 10 hours, the pattern is, I think, reproduced in 90% accuracy. So that's one thing. But the other thing is that in terms of this positional readout and positional and processing of positional information, it seems that early on, the morphogen gradients, they cover really well the tissue. Saying like here, in this case, this was a bit, over-exemplified, that you have this huge error in, early stage of the mouse embryo. Those overlap quite well in the center. And that's why you have also enough signal. And that's why my understanding is that in spinal cord, you really early on have a lot of this positional information, and then that's the important stage when this is read out. And also my later research points out that later on when it grows, it basically scales the pattern. So the growth is scaling the pattern, but the pattern was already there.
Okay, just one more. So, how do I put it? So in the case of, I think I'll ask you later. I think.
Yeah, we could continue. Also, I started a bit later, but I still think we should go. Have lunch, because lunch is great opportunity to discuss as well. But yeah, I'm here towards the end, or I'm here the full day, so I will be around. By evening, basically. So if someone wants to catch up, just catch me. And also, if something pops up to your mind, I'm not here, then just write to me, and I will be happy to reply.
Okay, so if not, let's thank Marcin once more. And before we break for lunch, let me remind you